All right. Good morning, everyone. Welcome to another seminar in the Livermore Finite Element Seminar Series. Today, we honored to have Professor Freddie Witherden from Texas A&M University here. So Freddie got his degrees at Imperial and has been at A&M Ocean Engineering.
Yeah.
For about 5 years now. Been involved in how the methods, bar codes, and coming to the SEED annual meeting. So a lot of interesting and relevant stuff for us. Today he's going to talk about small sparse matrix multiplications by code generation on CPUs.
Yep.
Yeah. All right. So Freddie, thanks for coming in.
Okay. Good morning, and thank you for inviting me. So today I'm going to be talking about some work that I've been doing with Intel around how can we accelerate small sparse matrix multiplication. And the way we're going to accomplish this is through code generation. To give a quick bit of motivation, small matrix multiplications, or FSSmMs, as they are often known, are a key building block of high-order finite element methods. So a way you can cast a large number of the operators which arise in a high-order finite element method, especially in their explicit variety, is as small matrix multiplications. Perhaps the canonical example of this is polynomial evaluation. So here on the slide, we have a triangular element, and working with a nodal basis representation, we have a polynomial defined inside this element at its set of points. Here we have a second order polynomial, so we have a total of 6 points. And let's say we wish to evaluate this polynomial at the following set of interface points. In the parlance of flux reconstruction, which is where I very much come from, the green points here would be referred to as solution points, and the blue points would be referred to as flux points. And the way things work out here is this operation, this polynomial evaluation or polynomial interpolation, if you prefer, in this nodal representation, can be cast as a matrix multiplication, where we have some operator matrix A, and then each blue point is a linear combination of each green point. And so long as you work in a transform space, this operator A is the same for all elements of a given type in your domain. And so what we have here is a small matrix multiplication, where the matrix A is small and fixed. It doesn't change as a function of time, and its values are known up front. And again, it is polynomial evaluation, but a large number of the other operators can also be cast in this form. Now, if we're working on CPUs, by far the most efficient library for performing these small matrix multiplications is libxsmm, which was primarily developed by Hans Pabst and Alex Heinecke at Intel. And what's notable about libxsmm is it does runtime assembly code generation. So it includes its own assembler, its own just-in-time compilation engine, and when you tell it, I want to do this matrix by this matrix, you give it the dimensions, it will just-in-time compile you a kernel to do that, and it is capable of not just targeting Intel architectures, but also ARM architectures. So of the major vector instruction sets, it supports AVX2 and AVX512 for Intel and AMD CPUs, and then on the ARM side, it supports the Neon instruction set and the much newer SVE instruction set. So developed by Intel, but it supports a large number of platforms, and RISC-V is also currently in development. But libxsmm is very much designed around the case where the A operator matrix is dense. This occurs in simplex elements, which is all well and good. However, it is also very possible for the operator A to be sparse. The canonical example of what gives rise to sparsity is when your element has some form of tensor product construction. We have an example of this. We have a quad here. We have some solution points and some flux points. Again, following what we normally do in flux reconstruction, where we do collocation projections, you'll notice that the solution points are not coincident with the flux points. These are all Gauss-Legendre rather than Lobato points. And with this, let's again consider the case of polynomial interpolation, where we want to interpolate to these two blue points here, with all the other points being grayed out. Thanks to the tensor product construction, everything couples along a line, and so each of those two blue points only depends on 3 of those green points. The result is that our operator is sparse. 2/3 of each row of our A matrix here will be zeros. The other case where sparse operators can arise is through the factorization of operators which may initially seem dense. So a good example here is we wish to interpolate to these blue diamond points. This would typically come up in flux reconstruction parlance. We would say when you're doing anti-aliasing, or some people say if you're doing a Galerkin projection, you want to interpolate from your solution point to some set of quadrature points, the quadrature points here being the blue points. And at first glance, this operator appears to be dense, but we can factor it in a way that leads to sparse operators. Specifically, if we introduce a new set of points, these yellow squares, judiciously chosen, then what we find is that to go from the green points to the yellow points, well, that is very clearly a sparse operator. Each yellow point only depends on 3 green points. And then again, to go from the yellow points to the blue points, that's once again a sparse operator. Each blue point only depends on 3 yellow points, and so one dense operator has been factored into 2 sparse operators. So these sparse small matrix multiplications can be quite ubiquitous in any finite element application that involves tensor product elements. Traditionally, the library that's been used for handling it is a library I developed when I was a graduate student called GiMMiK, or the Generator of Matrix Multiplication Kernels. It was originally designed with GPUs in mind, but was later extended to CPUs, and generally speaking, it takes a pretty simple approach. You give it an operator matrix A, which is sparse, and it generates C code that unrolls all of the dot products and eliminates, multiplies through by 0. The result is C code, which is then fed through a C compiler that hopefully encodes our sparse operator. So relatively simple C code generation. Matrix goes in, C code comes out, and all it's done is fully unroll the matrix multiplication through by A and eliminate any terms that are multiplied through by 0. The problem with GiMMiK, however, is that performance is unpredictable, as you're very much at the mercy of what your C compiler decides to do. In addition, for some larger operators, and by large I mean order, polynomial order 4, 5, 6, the kernels can take several minutes to compile and require gigabytes of memory. The resulting kernels are actually reasonably efficient, but that process itself is quite finicky, and you often need lots of poorly documented compiler flags to tell it to keep going, really try and vectorize this kernel, you can do it. And it can be done, but again, it's not good for usability, and you can get odd out-of-memory errors. So, not ideal. So, what I'm going to talk about today is how we've done it better. And what we've done in particular is add a fixed size, sparse, dense matrix multiplication routine to libxsmm. What does it do? You give it a fixed size A matrix, and it will generate a kernel to do A times B plus beta C, where A is a matrix of dimension m by k, B is a matrix k by n, and beta, our constant, is 0 or 1. You give this routine your A matrix and what value of beta you want, and it will generate a kernel. And it will be able to take advantage of any sparsity which is present in the A matrix, unlike the existing routines in libxsmm, which just JIT a purely dense kernel. So, what is our very rough idea here of terms of reference? Well, firstly, this isn't too controversial. The matrix A is sparse, because if it was dense, libxsmm has already got you covered, and it is invariant. That is to say, we are going to be performing the associated multiplication repeatedly, so we can take a little bit of time at startup to get a good kernel that encodes this operator. Next, I'm going to say that the matrices B and C are stored in row major order. This again isn't too controversial. Some of these ideas can be translated to column major, but when you're working with moderate order finite element methods below P7, P8, row major is the best way of arranging things in memory, and you'll see why this works in a second. Second, and this is a little bit more controversial as a requirement, the matrices B and C are small enough, that is to say, the number of columns in B and C, or the n dimension of the matrix, is sufficiently small such that they can reside comfortably in the L1 or L2 cache of a core. The final requirement we're going to make is that the number of columns in B and C is a multiple of the SIMD vector length, which I'm going to denote by VL. So depending on what platform you're running on, this could be 2 if you have 128-bit vectors and are working with double precision numbers, or it could be 16 if you have 512-bit vectors and are working with 32-bit single precision numbers. Practically speaking, these two requirements here are effectively saying that your code is cache blocked. That is to say, when it does its memory allocations, rather than allocating big arrays, it allocates lots of small arrays. This is good for a whole variety of reasons, and a couple of years ago, at I think the 5th SEED annual meeting, I gave a presentation on cache blocking and why you want to do it. And so if your code is not currently cache blocked, no need to watch this talk, just go ahead and cache block your code, because it will get you around 3x in performance, and then come back and watch the recording and learn how this will get you even more performance on top of this. But the fundamental idea is that all of our matrices are small enough to fit in cache, as this gives us good locality of reference, and it avoids all kinds of issues and quirks with CPUs. So these are our assumptions that we're going to be working with when we design our kernels. The only two controversial ones are the bottom two, but again, that just says cache block your code, as it really pays off, at least on CPUs. So with that, what is our approach going to be? Well, it's pretty much the same as GiMMiK. We're going to try and unroll our operator A. So in kind of pseudocode, we have an outer loop over the columns of B, where the trip count is n divided by the vector length. And then the inner loop encodes our matrix vector product, where we loop over each row in our matrix A, and then we do the sparse dot product. So this here is the loop we are going to fully unroll. And the most interesting part is this sparse dot product function, where you give it a row of A, you give it columns of B, and it is responsible for doing that dot product efficiently, and then all that's left is to write it back into an output matrix C, maybe with a factor of beta, depending on the application. So what we need is the orange bit. How do we come up with an efficient sparse dot product implementation from a code generation perspective? Well, we can consider doing all of this naively, so we can fully unroll everything in green. The sparse dot product, we can just issue instructions that multiply through every non-zero value in A by the appropriate value in B, accumulate our dot product, and then write it out. That's one very simple, very crude way of doing code generation. However, one potential issue with that strategy is if we unroll that loop in green, then we're only accumulating a single dot product at a time. We do one row of A, then the next row of A, then the next row of A, then the next row of A. And to understand why this can be a problem, if we consider an in-order CPU, which can issue 2 fused multiply add operations every clock cycle, and those operations take 6 cycles to complete, so you issue a fused multiply add, but you can't use the result until 6 cycles down the line. If you want an example of such a CPU, that is pretty much what the original Intel Xeon Phi, the accelerator card held together with BlueTech, was. And you work it out, you are limited to 8% of peak flops. Because you're only accumulating one dot product at a time, you're doing linear accumulation, takes 6 cycles to get the result, 8% of peak theoretical maximum, no matter how efficient we are with everything else. So, the good news is that all recent CPUs incorporate a technology called out-of-order execution. In other words, as they're looking at the instructions to be executed, they're looking ahead, and they're trying to find other work to be getting on with. So while we may only be accumulating one dot product at a time, the CPU can see in the code stream, because everything is unrolled, that there are actually multiple independent dot products in that code stream, and it will start working on all of them in parallel. And it will do this without any user intervention required. However, this only works if a reasonable number of complete dot product operations fit within the out-of-order execution window of your CPU. And this can vary. At the low end, you have something like an A64FX, which only has a window of about 40 instructions. And on the high end, you have something like an Apple M1, which can have north of 600 instructions. So again, if that window is big and the dot products are small, the CPU can go ahead and find lots of other work to be getting on with, and you can get 100% of machine peak. If that window is small and your dot products are big, you can get into trouble. So, how can we work around this? Well, the simplest option is to try and work on more dot products at the same time. Give more independent dot products. The simple solution for this is called N blocking. where we unroll some number of iterations of the outer loop, and then we interleave them. So if we do a factor of 2 n blocking, then we then have 2 dot products interleaved with one another. That's twice the explicit parallelism that we're feeding to the CPU. And that's just done by unrolling some number of iterations of the outer loop and then rearranging the instructions so they're all nicely interleaved. Immediately, you double or quadruple the number of dot products you're accumulating at the same time, but with a caveat. Your executable is now 2 or maybe 4 times as large. Because you've unrolled the loops, you've got more instructions. In addition, n, that is to say the number of columns in A or B, must now be divisible by n times the vector length, where n is the amount of n blocking you're doing, at least if you want to get good efficiency. This is one strategy we can take to get more explicit parallelism. A better solution is called M blocking. And the idea here is we have multiple rows in A. So rather than just doing these iterations linearly, let's try and interleave the dot products with one another. So rather than working on a single row of A at a time, we're working on multiple rows of A at the same time, multiple dot products being accumulated, hence more parallelism. And the nice thing about this technique, known as M blocking, is that all we're doing is rearranging existing instructions. That loop is already being unrolled. All we're doing is interleaving those instructions. So there shouldn't be any increase in code size. However, if it's to be effective, the dot products we interleave need to have similar numbers of non-zeros. If you've got one dot product with 6 terms and another dot product with 25 terms, then one of those dot products will finish before the other. So some care is required in terms of what dot products we choose to interleave. This is relevant for prisms, as I'll talk about later. The best case, however, is if we can find rows of the A matrix with identical non-zero structures, because then we can reuse bits of B because 2 dot products we're accumulating both need identical data, and so we have some advantages here in terms of how we're able to save cache bandwidth by reusing values from B. Now, these are some high-level strategies. In practice, the absolute biggest issue when generating these kernels, and it's also at some level the biggest issue to face compilers, is register allocation. What do you store in your registers? Once you know how you want to arrange things in registers, actually generating the assembly is almost a trivial exercise. It's completely formulaic, no thought required. What matters is what do you decide to store in your very limited number of registers. And this is what makes or breaks your performance. And so, from here on in, we'll be focusing on registers and how do we choose what we keep in registers and what we have to load in from cache. And the answer here depends very much on what hardware you're targeting. So, we'll start with the oldest instruction set, which is the AVX2 extension to Intel and AMD GPUs. This has been around for about a decade now, and what it gives us is 16 logical registers, each of which is 256 bits. So we have 16 registers to play with. Additionally, AVX2 gives us instructions for doing A times B, which is a multiply, and we can also do C plus A times B, a fused multiply add, where with the FMA, we have the ability, should we wish, to negate signs. This, as I'll explain in a second, turns out to be very useful. Finally, a very nice part of the Intel architecture in general is that register B doesn't have to be a register. The argument B to these instructions can also be an address in memory. And it can take the form of G plus IMM, where G is just a general purpose register. Think of it as a pointer. And IMM can be basically any number you like. And that can all be encoded in the instruction. So we can say multiply register A by this pointer in memory plus this displacement, all in one instruction. Okay, so this ability here to negate the product A times B effectively means that when we're looking at our matrix A, which is the sparse fixed matrix, we only need to concern ourselves with unique absolute values, because we have the ability to negate constants in the instruction itself. So, following on from this, let's give our first strategy. If we have 15 or fewer unique absolute values, so we look at our matrix A, we look at the number of unique numbers in that matrix, we take their absolute value, and if that is less than 15, a very simple strategy is to store one unique value of A per register. And then our final 16th register, or any other registers that are left, can be used as accumulators for our dot products. We term this the A in registers approach, as the matrix A, or rather its unique absolute values, are stashed in registers, and whatever's left can be used as accumulators. In practice, this gives us the following register map. So if we have 6 unique values, that's U6, and we aren't doing any M or N blocking, then we have 6 registers, 0, 1, 2, 3, 4, 5, holding values from A, and then we have 1 register that is used for accumulating our dot product. We move, in the case here, I'm showing in the second row, 9 unique absolute values, and we'll do some N blocking. So now we have 2 registers that have to be marked as accumulators for our dot products because of the N blocking. Alternatively, if we wish to do M blocking, we again have 2 accumulators, but we also allocate an additional register to hold a value of B. The idea being that if 2 dot products both need the same value of B, rather than having them both loaded from memory, we issue a load instruction to bring it into a register, and then we do 2 operations, all involving registers, as it's more efficient to do 1 memory access into a register, and then 2 register operations, than have 2 operations that both bring things in from memory. So it's an optimization, but it's an optimization here that costs us a register to hold a temporarily loaded value of B. So this is what the register map looks like, and this works up to 15 unique absolute values. What happens if we go beyond that? Well, when the number of unique absolute values exceeds 15, we store the unique absolute values from A in an array. And then, when we're generating our code, we load those values in from memory in advance from when they're needed. This is done using a broadcast instruction, which loads a 4 or 8 byte double from memory, and then broadcasts it to all lanes of our vector. We term this the A in memory approach, as the unique absolute values are stored in memory. The overall idea here is that we figure out how many registers we need for our accumulators, and for holding B, and then all remaining registers serve as a cache. That is to say, rather than always loading in the unique values of A from memory, we try and keep them around in registers. This works pretty well because we have knowledge of the future. I know what dot products are going to come in the future. I know what unique values they contain. And so when it comes to our eviction policy, we have perfect foresight. And thus, when we need to load a value in from memory, we can look at the values we currently have and we ask the question, which value is not going to be needed in the future or has the longest distance between now and when it's next needed, and we can choose to evict that value. Again, this is an advantage you have when you do code generation because you know what's coming ahead of time. Thus, we get the following register map where we have our accumulator registers, potentially a loaded B value register, and all of the other remaining registers are marked as temporary registers to hold unique values of A that we brought in to memory, and they are managed according to the cache replacement policy that I just described, wherein we know what values are going to be needed in the future, so we can be smarter than a typical cache which doesn't know what's happening next. So this is the A in memory approach, and it scales in principle to an arbitrary number of unique values. So that's AVX2. In 2016, Intel moved things forwards with AVX 512. The headline additions are we went from 16 registers to 32, which is extremely useful, and those registers also doubled in size. But it's the additional number of registers that really makes a difference here, because now we can increase either the number of unique absolute values that we can keep in registers from 15 to 31, or for the A in memory case, our cache has just doubled in size or nearly doubled in size. But Intel also gave us another neat feature with AVX 512. What we got was some very flexible permutation instructions. Permutations giving us the ability to swizzle data around in vector register. In particular, we gain the ability to store multiple unique values inside a single register, albeit with a slight caveat. If we store values packed in our registers, before we use those values, we need to extract them. And to extract them, you need to do these permutations, and these extractions require permutation constants. And what this means is that for this approach, where the matrix of A is packed inside registers, what we get is we can store 8 double precision values in a register, they're 512 bits, or 16 single precision values. That's really nice. However, extracting these values from their registers, which we need to do before we can use them, requires these permutation constants, of which you need either 7 or 15 of. In practice, in both cases, single and double, you can support up to 120 unique absolute values in registers before we need to go out to memory. To explain how the permutations work, let's say we have a register here. It's going to be double precision. It has 8 constants. Then I'm going to define another register, and it's going to be filled with this repeating pattern 4, 5, 4, 5, 4, 5, 4, 5, 4, 5. Then we have an empty register, and I'm going to execute this permutation instruction. And what this will do is it will say the first 4 bytes of 31, it goes along to register 8, looks at the first entry, and it says that's 4. So it will pick the 4th value from ZMM0. We do the same again. Picks the 5th. And so what that effectively has done is it's broadcast the 3rd constant in ZMM0 into the register ZMM31. Again, this instruction is incredibly flexible, as it can do arbitrary reordering and duplication with 4-byte granularity. What we get is this rather elaborate register map, where we have our constants packed in registers. Then we have permutation constants, which are used to extract them. And then a cache, they're the purple registers, which are used to hold the values that we've pulled out of our registers. But again, what you can see is this allows for things like 40, 49, different values, all to be stashed in registers, so we never have to go out to cache to get our A values. Instead, we just execute these very low latency permutations, and they extract the values from the green registers into these temporary purple registers using the blue constants. The number of constants you need varies, as you can get some situations where you don't always want to pack, say, 8 values into a register. Sometimes it's better to pack fewer values, as that means you need fewer permutation constants. And so when you solve the optimization problem, you can get a lower overall number of registers, sometimes by packing less. Okay, so that's AVX512 and the rather neat strategy that it allows. We're now going to look at ARM. We're going to look at the traditional vector instruction set called Neon, which gives us 32 128-bit registers. And we get our usual set of instructions for doing A times B and C plus minus A times B. But since ARM is a RISC architecture, A, B, and C must all be registers. We can't do memory operands inside arithmetic instructions. However, ARM in Neon does allow us to play a really neat trick. It supports indexed forms, where effectively you can say C gets the value of AI times B, where AI is a specific lane of a vector register. So what it will do is it will broadcast the ith lane of A and then do the multiplication. What does this mean for ARM? We can implement that A packed in register strategy that I just described for AVX512 for free. Just because the instruction set allows one of the arguments to be indexed. You can say, multiply everything not by this register, but by this lane of this register. Really neat. However, since ARM is RISC, we have to go and load things from memory. And one of the caveats is that we have very limited displacements. A consequence of this is that what we can load in a single instruction in AVX512 can sometimes require 5 instructions for ARM. It can take 2 or 3 add instructions to generate the address in memory. Then we have to issue a load instruction to load whatever's at that address into memory. Then we have to do the FMA itself to do the multiplication. One AVX512 instruction can hence translate into 5 ARM instructions in the worst case. But again, this depends on how big your immediate displacement is. Smaller displacements often require fewer add instructions, but it can be as bad as 5 instructions. But the ARM developers are pretty smart people, so they help us out a little bit. What they give us are paired load instructions. effectively, we can load 256 bits at a time. So although it's a 128-bit vector instruction set, we have the ability to load 256 bits at once. You just say, here's the address, and here's a pair of registers, and it will do 2 loads in one. What this means is that for Neon, this n-is-2 blocking suddenly becomes very attractive because you want to work on 2 times the vector length because you get these highly efficient paired loads, and that means you have reduced overhead in terms of figuring out addressing. And that in turn increases your FMA density. So what do we get then in something like Neon? Well, I'm showing a lot of examples here, but they're not particularly interesting beyond the first. Let's say we have 8 single precision values, registers 128 bits. We can stash 4 values per register. So we need 2 registers to hold our packed A values. Then we always need a register to store our loaded B value, always, because it's a risk. And then we have 1 accumulator. Here we move to the case of n-is-2, and that's when we start breaking out these paired loads. So we now have 2 accumulators, nothing wrong there. We have 9 single precision constants, so we need 3 registers to hold those constants. And we now need 2 registers for our loaded B values because we're going to be loading 256 bits. So it costs us an extra register, but it's absolutely worth it for the efficiency savings. And again, I'm just showing some more examples down here where you can go as far as have n-is-4 blocking with m-is-3, and that gives you 12 accumulators, which is often overkill. And again, double precision, we're a bit less efficient because our registers now only hold 2 unique values rather than 4. But again, this is our overall register map. The interesting thing being how we can always store things packed in memory with no overhead. Now, let's look at the A in memory case. What happens when we just run out of registers to hold our unique values? Well, it looks like things aren't that great because we don't have great support for immediate displacement when we do loads from memory. We have to do all these add instructions and arithmetic on our pointer to get the address in memory that we want to load the value in A from. But again, the people who designed Neon were pretty smart. And we've got 2 really cute tricks. Firstly, there is an instruction called LD1, and that allows us to load a constant from memory into a specific lane of a vector register. So rather than broadcasting it, we can say, load this into the 3rd lane of register 5. Thus, we can always work in packed form. What does this mean in practice? We can cache 2 or 4 times as many constants in registers as AVX512. Same number of overall registers, but in ARM land, we can do things on a lane-by-lane basis. Very neat. Secondly, ARM has support for something called post-indexed forms. And this is best described with an example. We have an array in memory, and we have a pointer in a general purpose register X5 to an address in memory. I then have a vector register V5, we're looking at single precision, it's got 4 numbers in it. And we're going to execute this instruction, LD1 V5S1 X5 4. It reads like a bit of a mess, but it'll make sense in a second. This will load the value in X5 into the first lane starting from 0 of the vector register 5, treating it as single precision, and then it will increment the pointer. So it does this. It does the load into that specific lane, and then it post-indexes. It marches our pointer forwards 4 bytes. 1 instruction. Thus, by getting a bit creative, and we have our array in memory that contains not just the unique values, but the values in which they are needed by the kernel in terms of cache misses, then we can bring in a constant with just a single instruction, always. The idea being that the array is arranged in memory such that it has all the constants in all of the order that they will be needed by the kernel, and then bringing that constant only ever requires one instruction, 4 bytes, highly efficient. It does mean that our array has some duplicated values, but that doesn't really cost you much. In practice, we can handle having some duplication in that array. Thus, we get the following register map, where again, our temporary values, that's our cache, they're all packed, so we can store a huge number of temporaries, and then we just have our loaded B values and C accumulators. So, very nice. Now, on to something that is not so nice. This is SVE, the latest and greatest vector instruction set for ARM. And its claim to fame is support for varying vector lengths, from 128 to 2048 bits. The scalable functionality in being able to use the code on machines with different vector lengths, that doesn't matter for HPC. We always recompile, and so the scalability is a nothing burger for us in practice. But we do like longer vectors. That means we can be more efficient. So, where does SVE leave us? Well, index forms are carried forwards, which doesn't seem to make a lot of sense when you think that it's meant to be scalable in terms of the vector length. However, this was worked out by doing things in 128-bit chunks. So, let's say we have SVE 256, so 256-bit vectors. So here's a vector, A, single precision. 8 numbers in our register. The index form A0 effectively gives us the following, where the first lane has been broadcast to its 128-bit group, and similarly that red value has been broadcast to its 128-bit group. So everything is being repeated on a 128-bit basis. We have A1, A2, and A3. Thus, indexing still kind of works. We can still play these same tricks, as it's just done on a 128-bit chunk basis. We can still get a value broadcast from my register. And SVE helped us out a little bit here with something called replicated load instructions. LD1RQW. I don't know how you pronounce that, but what it does is roughly as follows. Let's say in memory, we have 4 single precision values, and we have a pointer to those values. Then we have a register. I'm going to say SV512, what you find on an A64FX. And then we're going to execute this replicating load. What it will do is it will load from x26, and then it will replicate it on a 128-bit chunk basis to the remaining parts of the vector. Don't worry about this P0 thing. This is just because SVE supports some form of predication, and you have to say what predication you want, but that's not relevant here. We just want to do a load, we load 128 bits, then it replicates for us. So this way, index forms, packing values in registers, still works, with one exception. Bizarrely, and this is very unusual for ARM, indexing is only supported for the first 16 registers at double precision, or the first 8 registers at single precision. So in the instruction, if you're doing an index form, the register has to be a certain number or less, or it doesn't encode. So you work it through. When the number of unique values exceed 32, we need to figure out what to do, as indexing kind of doesn't work. Our solution here is we allocate the first register as a temporary. And then if we need to do an operation with a constant stored in a higher numbered register, we first issue a move instruction to copy that register to a low numbered register, and then everything works as expected. The good news here is that on modern architectures, register-to-register move operations are free. They cost you code size, but they don't consume any execution resources. So it looks like a bit of a nasty hack, but in practice, performance isn't badly affected. What this gives us is the following slightly gnarly register map. It's very similar to Neon, except you can see here, when we go to 33 values, single precision, we need to allocate this register 0 to serve as a temporary register. And so if you need something, a constant in register 8 or register 9, we first copy register 8 or register 9 to the temporary register, then we issue the instruction as normal. And again, that means when you're doing your register allocation, that you want constants that are used more frequently to be in lower numbered registers, because that reduces your code size. Again, not ideal, but we still get to pack values in registers, so it's still a win. Now, let's look at the A in memory case. This is something that worked out really well for Neon. It does not work out well for SVE, as we don't have a replicating load instruction that is lane indexed. We can't play that same trick that we played with Neon. You would think that predication would allow us to work around this. We could say, do the replicating load, but mask out all of the lanes we're not interested in. Unfortunately, the replicating load instruction only has support for zeroing masked lanes rather than merging into them. This is a big deficiency of SVE compared to, say, AVX512. Predication often means we zero anything that's masked out rather than leave it alone. Okay, so we need a compromise solution. What do? Well, we try and cache one unique value per register. So in other words, we do what we do on Intel. Each register just holds broadcasted constants. And the only thing we can do to reduce the amount of effort required for loads is, for these arrays, SVE gives us the ability to load with a 64 value displacement. So if we have our general purpose registers pre-displaced by 64 values, then we only need a single load instruction. As we have lots of general purpose registers all pre-displaced, so we can do our load with one instruction. It's not perfect. We burn through a lot of general purpose registers, and if you run out of general purpose registers, then suddenly you have no option but to do lots of pointer arithmetic. It happens, but it's the best we can do. The result is a register map that is pretty much identical to AVX512. We have our temporary broadcast A values as our cache, loaded B values, and C accumulators. Okay. Now, it should be clear that we often have freedom when it comes to how much M and N blocking do we want to do. Sometimes that can mean a bigger code size, or we need more registers to be used as accumulators. And it's often not clear what gives the best results. So the way we handle this in FSSpMDM is through auto-tuning. We can generate kernels in milliseconds. So we just generate a bunch of kernels with different strategies, we auto-tune them, and we see which one works best. And we do that at runtime, so it's based off the matrices you'll be working with, their dimensions, and the hardware you're running on. And it seems to work out very nicely. So we just try a bunch of different M and N blocking factors. we auto-tune, and whatever gives us the best result, we go with. Okay, so in the last 5–10 minutes, let's talk results. And I'm going to be evaluating our kernels with the operator matrices that resolve when solving an advection diffusion type problem, Navier-Stokes, using the PyFR solver with a quadrature-free numerical scheme and a collocation type projection with Gauss-Legendre type points. So this is a pretty canonical situation that arises for a lot of our real-world simulations. In terms of element types, tetrahedra are dense, no need to think about them. They're already handled. Pyramids. Nobody cares about the performance of pyramids because in general, you have a single layer of pyramids in your domain as a transition element. The performance doesn't matter. In terms of scaling, the number of pyramids in your mesh is order 1. Irrespective of how much you refine, you'd have many pyramids. So what we have left are prisms and hexahedra. 2 good elements that you get a lot of. And I'm going to go with the case that the number of columns in B is 40. What that means, why 40? Why is it such a magical number? That corresponds to 8 elements per block with compressible Navier-Stokes. Compressible Navier-Stokes, you have 5 field variables, density, 3 momenta, energy, 8 elements per block. That gives a case of n is 40. There are other values, but this is the one that arises the most in our cache block approach, as it's what other kernels, such as interface kernels and flux kernels, benefit the most from. So, let's now look at our matrices and how they line up. This is quite an informative plot. Log, what we have are the number of non-zeros in the various operator matrices down the bottom, and then the number of unique constants along the y-axis in terms of an absolute sense. The color of each point corresponds to the polynomial order, 1, 2, 3, 4, 5, 6. Circles are hexahedra, triangles are prisms, and then the density of the matrix, as in what fraction of its values are non-zero, are illustrated by the size of the point. So you can see prisms, triangles, are denser than hexes. No surprises there. Hexes are very sparse. They never have that many unique constants. It's always less than 30. And then these terms, M0, M6, M1, M132, M460, these are just the internal PyFR terms for things like our volume to surface operator, local divergence, divergence correction, local gradient, and gradient correction. Of these two, M3 and M6 have beta equal to 1. The rest have beta equal to 0. Okay, so with that, these are our matrices. Let's now look at some performance results for these matrices at various orders. First up, we're going to do AVX2 on a recent Intel CPU with a Golden Cove core. Orders 1 and 2 are completely uninteresting. You can do them dense and not lose any performance because they're so small. And what we're looking at along the y-axis is gigaflops per second. That line, that dotted line, is machine peak for a single core. That is single core peak. That is as fast as you can hope to go. And what we're comparing is FSSpMDM in green against GiMMiK in orange. And apart from the M3 matrix, which you can ask me in the questions about later, we do a pretty good job, especially at higher orders in these hexahedra, outperforming GiMMiK. And again, the hexes really are the easy case because you don't have that many constant unique values. but we're still able to deliver quite a nice win against GiMMiK, and again, with low compile times. Let's now go to an M1 max. So this is neon quad issue. It's what you'll find in recent Apple chips. And you can see here that for certain matrices, our win is actually quite a bit better. M3 is still giving us some grief, but for other matrices, we're getting almost twice the performance, and in many cases, getting quite close to machine peak of about 52 gigaflops on a single core. And almost all the operators are getting close to 50% of peak. And again, this is 50% of machine peak for a sparse matrix multiplication, only counting non-zero multiplies. So now let's move on to prisms, which are a bit more challenging because they're denser. And you can see here that our lead, this is goes, did I?
I think it,
That's just a, sorry, it's a typo. That should say Intel. These are Intel results. But you can see here, yeah, this is Prism, sorry, yeah, this is Prism M1 Max. You can see here that we are delivering substantially better results than GiMMiK, often by a factor of 2 for these Prism operators at orders 3, 4, 5, 6. Again, a big improvement, and this is on the M1 Max. Let me check. Okay. Yeah, okay, sorry, I skipped over one of them by mistake. So that's hexes M1, and again, you can see here that we're getting a nice lead, but M3 is still giving us problems as it did on Intel. But something like M0, which you actually end up applying quite a few times, we're getting a good win. And on prisms, you can see here on the M1 Max, we are doing much better than GiMMiK, often by a factor of 2. And again, we're getting in striking distance of machine peak for a sparse operator. So, in conclusion, we've described a new small fixed size sparse matrix multiplication routine that is in libxsmm, and have shown how it's able to outperform GiMMiK on Intel and Apple architectures, especially for prismatic elements. And if anyone wants to know why M3 is such a turd, I have some backup slides, but I don't know how we are for time.
all right, questions? Putting the folks online. Let me start with one. So this was really impressive speed ups, especially for the prisms. But this was just the kernels. What's the speed up in the overall simulation time?
It's a bit less because some of those kernels do go out to memory.
Yes.
And so it works out 20 to 30%, which is not as big as the speed ups because, again, some of those kernels, they aren't writing out to cache, they're writing out to memory bandwidth, and then GiMMiK is usually able to saturate the performance. So it's about 20 to 30%, again, depending on the order, which is a respectable speed up when you account for the fact it also gives you a usability advantage, because you don't need to spend gigabytes of memory compiling, and a lot of work is needed to get GCC to vectorize those kernels. Clang won't even try. So in practice for our users who often, how can I put it politely, don't know all the esoteric compiler flags to tell GCC to really try hard to vectorize, the speed up is a lot more. But in terms of a perfectly fair comparison, between 10 and 30%, again, depending on CPU order and everything else. The main reason this was done, though, is for tensor product factorization, because there you have back-to-back kernels all executing out of cache, and there the straight line performance of the kernel really matters. If you do tensor product factorization as a sequence of kernels, right, which we're usually advised not to do, but if you're cache blocked, it's okay, there the kernel performance does matter because the inputs and outputs are all in cache. Because it's one kernel, another kernel, if you say factor a hex, and there the performance of the kernel really becomes important. but we still are just about to submit the paper on that. So it was more written for that sparse factorization case, because there the individual kernel performance really matters.
Okay. All right, thanks. So I see Colby has a question. Colby, do you mind unmuting and asking? Does the auto-tuning run the code and time it to examine the instructions or something else?
So it generates all of the kernels, which basically end up as function pointers once they've been jitted, and then it benchmarks them competitively.
Okay.
And we also have a get out that if the dense kernel is within 10% of a sparse kernel, we go with the dense kernel. As the advantage there is dense kernels are smaller, that puts less pressure on your code cache. And that means other kernels can fit in. So on the AVX or some of the Intel results, practically speaking on Intel, once you leave the micro op cache, you're limited to 16 bytes of code can be decoded per cycle. And some of your FMAs can get up to 10 bytes, which means dual issuing FMAs every cycle on Intel is very challenging due to code size limitations if you go out of the micro op cache, which is only a handful of instructions. So code size really matters.
Yeah. Yeah.
And that's often what's limiting our performance here, is we're decode limited. Intel will tell you in their marketing material, this chip can decode 32 bytes per cycle. But if you ask Intel, they say, yeah, that doesn't actually work and it's flipped off in the production CPUs. So on their marketing material, that chip should be able to do 32 bytes per cycle.
Yeah.
In reality, it's buggy, it's 16. But if it was working as intended, most of these things will be hitting straight peak, would be dual issuing.
Okay.
And I showed AVX2 because it actually shows us in a worse light, because you've got fewer registers.
Right.
And we're smarter than the compiler when it comes to register use, but in low register scenarios, the compiler is about as good as us.
Right. Okay, other questions? The folks on?
Yeah, I mean, what's the limit in size of, I guess, in terms of polynomial order?
Yeah, so I went up to P6 here. You could do P8. Beyond that, I think you want to change the data structure, as we're currently getting parallelism in the vector sense by working on multiple elements or multiple field variables. That's where this 40 came from,
Yes.
which was 8 times. When you get to higher orders, I would say you want to try and get your parallelism inside a single element,
Right.
which means you do some preloading, you do some transforming, and then you crack these kernels further into line-by-line operations, and then you run multiple lines at the same time. But you try and get your parallelism inside a single element by doing some data layout transformations before you start executing the kernel, so you can get multiple lines, and then you can maybe run 8 lines at once, depending on the order. So I do a slightly different strategy. In terms of this strategy, this data layout, these kind of P's are sensible. Beyond that, I think you want to start changing your memory layout.
So you said this is all implemented in libxsmm?
Yep.
Is it freely available? Is it straightforward to use?
Very straightforward.
Okay.
You just give it your matrix, and it gives you a function pointer.
Okay.
Pretty much.
All right. Another question from Jonah. Do you want to ask it or should I ask it for you?
I can ask it as well.
Yeah.
So my question was, if you have looked at the other architectures like IBM Telnum or AMD Genoa, which recently came in with a lot of more cache.
Yeah, so here we're working very much at the L1 and L2 cache. And so there, while you definitely get benefits in other kernels that do indirect accesses, here we're working very much in terms of the L1 and L2. And so there are no big benefits there from having more last level cache, as that last level cache is pretty slow. The L1 cache on a recent Intel CPU can deliver 128 bytes per cycle per core, whereas if you look at, say, an L3 cache, that might do 128 bytes per cycle to all of your cores. And so by the time you've left your L1, your performance is just completely roofline limited by memory bandwidth. And that's why you want the cache block, so you're living out of your private caches. We haven't really looked at IBM, as for all intents and purposes, they're out of the HPC game. in terms of episode.
Being recorded.
I mean, they're not trying to sell Power 10 CPUs for compute, but we are looking at RISC-V, and as those chips begin to come online, I will get this updated to the various RISC-V, as that I am optimistic about in terms of having a volume product, shall we say.
So on the ARM side, you showed the Apple chips, but can you comment in general about other ARM chips?
Yeah, so on the SVE side, there's A64FX, which is, okay, this is being recorded, it's a bad chip. It is worse than the second generation Xeon Phi. In terms of the number of quirks, it is objectively a bad chip. It may not as well not even be out of order, and they ain't selling any more of them. But there are some good chips with SVE. The best SVE chips you can get are the Graviton 3s. Mm-hmm. They have a very, very nice implementation of SVE 256. There's just one caveat on the AWS side, which is where you have to currently get them. Mm-hmm. And that is that FMA operations are throttled across the chip. And so doing benchmarks on them is an absolute nightmare. So your code may be able to get peak, but the chip globally caps how many FMAs it can issue per cycle for power reasons. And so doing benchmarking is a bit more involved, and you have to get an exclusive instance.
Okay.
It's a quirk, but that's what we did all of the SVE development on. We gave up on the A64FX, but the Graviton 3 is a very nice chip. Okay. It's very impressive. It has a good implementation of SVE, and we do get good results, but benchmarking is difficult because of the FMA issue rate.
Okay, thank you. All right, any last questions? Okay, let me just say, Freddie is here today and tomorrow. Yep. Or tomorrow morning at least. If you want to meet with him, if you want to join us for lunch, please let me know.
And if you have a couple of minutes, I can explain these M3 results.
Yes, please.
So this is an interesting one. So back up slide. So we noticed that on this hex M3 matrix, that GiMMiK was often outperforming us. And again, that's interesting. How is the compiler, with all of its constraints, able to outdo hand-tuned assembly? And the answer is M3 has something of an interesting structure. So it is the correction operator. So if you think about this point here, it takes contributions from these 4 points. So every single row in that matrix has 4 non-zeros. If this was a hex, we have 6 non-zeros. Doesn't matter the order. You can go to P a million, each row will have, in a hex, 6 non-zeros. Now, one other neat quirk. Let's take a look at the contribution from these 2 red points. In reference space, they are the same distance from the green point. And so their constant, the number, is the same. So this means there's an opportunity for common subexpression elimination. That's point number 1. Point number 2 is if you kind of work through this pattern, you will see that no 2 points share the same non-zero structure, as in every other row of that A matrix couples to a different set of blue points. Practically speaking, GCC, because it's quite a small set of dot products, exploits this, and it plays effectively 3 tricks. It does common subexpression elimination, which means it can use lower latency instructions. We're not flop limited, but again, adds a lower latency that multiplies. And when you've got small dot products and you use low latency instructions to accumulate, you only need to use a single accumulator register, and your out of order execution will find all the other work. So none of our M or N blocking stuff does anything useful. The trick it plays is it knows that there are always 2 values that can be reused along a line. In any direction you go, there are 2 values that all rows along a line will make use of. Thus, it makes sense to store 2 values from B in registers, and you get guaranteed 1/3 reuse. And the reason this matters so much on Apple is they can do 4 FMAs per cycle, 128 bits. but they can only deliver 32 bytes per cycle from their cache. So if you have to load 4 values from cache each cycle, you want to load 64 bytes. The chip will only let you have 32. That's actually inferior to Intel, where you normally have a 1-to-1 ratio of FMA to cache bandwidth. And so unless you're getting value reuse in B from registers, you'll be cache bandwidth limited on Apple. The compiler, because these kernels are so small, keeps multiple values in B in registers, whereas our strategies at the moment don't try and do that.
Yeah.
And it saves cache bandwidth, it beats us. We know what it's doing, we can work around it, and we can identify these kind of patterns and allocate more registers to hold B, whereas previously we've only been storing A. The question is it worth it? And that basically comes down to, would someone design an HPC-focused chip where you don't have enough cache bandwidth to satisfy all of your execution capabilities? Intel and AMD and ARM so far have kept that balance. Apple haven't, and that's why the compiler outdoes us. But again, it really comes down to the structure of these operators, and you have to dig in to see what's going on, and often they can actually be factored further.
All right. Last chance for a question. Okay, let's thank Freddie again.